Okay, this mini lecture is going to expand on the mini lecture on standing waves and look at some of the math related to the information that we get from a standing wave. How do we generate it? What's it related to? How can we represent it mathematically? So I have two images that kind of drawn up here. I have my fixed boundary and its first harmonic and second harmonic, two fixed boundaries. Then I have a closed and an open boundary tube where I have its first and its second harmonic. So slightly different because they are different entities and they produce standing waves slightly different. Both are the first and second harmonic for their respective, and we're going to look at how are these harmonics related to other properties of waves. So how are they related and the physical object that's making them, this boundaries with the waves on a string, or this tube or the air wave is being generated as a standing wave. Okay, so let's look at the frequency and its relationship to the physical element first. If we examine this fixed boundary, we're going to start there. We know that there's a certain length between these two boundary locations, right? We're going to define that at length as length L. And if I imagine this first harmonic, and I kind of visualize this blue, the standing wave being a full wave, if I were to look at the wavelength of that wave, remember the distance that a full cycle of the wave takes up, I notice that I go up, and if I were to complete the wave, I'd have to go back down and then back to, of course, that middle position. So this part of the wave represents 1/2 of the wavelength. I'm sorry, 1/2 of the length. The wavelength, I'll erase that. The wavelength is equal to 1/2 the length of the distance, or the distance between the two boundaries, or in our case, we call that the length L. For the second harmonic, the wavelength is equal to the length. I have a full complete cycle in that distance L for the second harmonic. So in a little bit of rearranging, we can look at these two and see how we can play with them. 2 times the wavelength is equal to L for the first harmonic. L is equal to the wavelength for the second harmonic. If you can visualize that third harmonic, I'll go ahead and draw it up here. I want you to think about, okay, well, how is the wavelength related to the length? These are not drawn very proportional, sorry about that. How is the wavelength related to the length in this third image? Go ahead and think about that. Well, pause the video so you can think about it. Okay, so we have 1.5 wavelengths in that length. So our wavelength is 1.5 wavelengths in that length, so 2/3 the length of our distance, 2/3 the length L. So we have 3/2 of a wavelength, so our wavelength is 2/3 of the length. Okay, that's great. We got some wavelength information, but remember the wavelength is related to the frequency, which is also related to the speed of the wave. So we're going to take this information and we're going to add in some information about wave speed. Now let's back it up a little bit. Wave speed, remember, was dependent on a few things. Actually, it's dependent on a very foundational thing. Now, whether it's a string or whether it's air, whatever, wave speed is dependent on the medium itself. So this string, under that specific tension for that distance, is what dictates the wave speed. So wave speed is a constant for this particular situation, right? So wave speed is dependent on the medium. We also want to keep in mind that wave speed is equal to the frequency times the wavelength. Remember, that's how we looked at that back when we introduced the idea of wave speed. So go ahead and check out that video if you are unfamiliar or forgotten how that's all related. If we use that information and we look at the wavelengths, I can now start to use this relationship to get an appreciation for how the frequency of the object is related to the length. And I find that for the fundamental frequency, if I simply substitute the speed divided by the frequency in for my lambda, I find that the frequency that gives me the fundamental wavelength is equal to the speed of the wave divided by 2 times the length. So that's just a math substitution. Go ahead and do that a little on the side if you want to confirm it. For my second harmonic, I find that the frequency of the second harmonic is equal to the speed over the wavelength. My second harmonic, we know the wavelength is equal to the length of the object. And for my third harmonic, we find that 3 times the speed, or 2 times the length, is the third harmonic. Well, this relationship, the speed over 2L, is simply my fundamental frequency. So this turns into, whoops, here's the right color. That turns into 3 times my fundamental frequency. So I actually can get a generic relationship for the harmonic frequencies in a standing wave on a string. And that generic relationship is for the fundamental frequency, the frequency for any harmonic n is equal to n times the fundamental frequency, where that fundamental frequency is equal to V over 2L. All right, so this is sort of my generic relationship. Now, does that work for frequency of the second harmonic, this generic relationship? Well, 2 times the frequency of the first harmonic, where the first harmonic is V over 2L, gives me V over L. So yes, it does. So this is our generic equation for the harmonics of a wave on a string. All right. What about waves in an open closed tube? In an open closed tube, and I'm going to go ahead and erase these just to avoid the confusion. First harmonic, remember, is, and we're just going to do a couple of these and then we'll sort of move on. The first harmonic, remember, is the lowest frequency to produce a standing wave. So, what do we have in this situation? Well, again, we have to sort of imagine the wave continuing on, and we see that the length, again, imagine this has a length L. The length L is equal to 1/4 of the wavelength. So in the case of the closed open tube, the wave 4 times the wavelength is equal to the length. Just like in the terms of our medium dictating the speed, it also dictates the speed. Here's the speed of air, and for the most part, of course, as you see in that air description, that conversation that we have just about qualities and description of sound and sound, and of course sound and air specifically, we tend to, at 20 degrees, we know what that speed is, but it's consistent of the medium. So if I do my same behavior where I plug in that the frequency is equal, or sorry, the velocity is equal to the wavelength times the frequency, I have for V over L is equal to my fundamental frequency for a wave, standing wave, in a closed open tube. Right? So I'm just plugging in lambda as V over F, bring the F over, bring the L down. For the first harmonic, I have 1 1/4 wave, right? So 1 1/4, 5/4 the length, 5/4 of the wave is equal to the length. And we can do a similar substitution for that open, closed pipe. Most important thing out of here is that we're recognizing that fundamental frequency and how to visualize that fundamental frequency. We're recognizing that's slightly different in a wave on a string or an open closed tube. And we're keeping in mind that we can relate it not only to the length of the tube or the length of the posts between the string, the length of the string, but also the speed, which is dictated by the medium, so the air, or if this was in water, the tube, the tension, and the mass density of the string for a wave on a string. Once we have that information, we can determine what frequencies are required in order to oscillate these objects in a standing wave. We'll do one last thing, and then it's sort of the conceptual ideas. Does this all make sense? From our experience, when I'm holding a wave on a string, if I'm holding a shoelace between my two hands and I start to shake it to generate my standing first wave, based on the math that we just talked about, the second harmonic, I'd have to shake it faster. And yeah, that's our experience, that we shake it faster to a certain specific frequency, 2 times the fundamental frequency, in order to shake that wave the appropriate frequency to get a second harmonic standing wave. And I gotta go a little faster, 3 times the fundamental frequency, to get the third harmonic. All right, so kind of some generic ideas about standing waves. In the next main lecture, we'll do a little practice problem using this information. Good job.